Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Starquake, published in 1986 by Bubble Bus, created by Stephen Crow, and the conversion was by Nick Strange. We're going to be looking at how this game fits 512 screens in a single load and also its sprites. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are always very much appreciated. This was a conversion from a ZX Spectrum game, but you'll notice that it's a version, or conversion rather, which uses the sprites on the Commodore 64. So we can see in the graphics map here that we have some dynamic sprites. We also have a couple of, actually three, overlaid single color high resolution sprites to form the main character. We've got eyes, the feet and the antenna, and then the main body, and each of those are separate sprites. So this conversion looks better than the original Spectrum version because obviously it doesn't have the color clash. It has more colors and the main character is more colorful than the original one. We've also got, well, it's a single buffer for a full high resolution bitmap screen, which is not really a surprise because this is a flick screen game. We've got the score panel up at the top in the same high resolution bitmap screen as the main game display. And we can see where the bitmap screen is, and we can see where the sprites are in relation to everything. The explosion particles, the transporting in aliens effects, the aliens, the main player character, and the platform that you're moving around on are all hardware sprites. They're not software sprites, like some other Spectrum conversions were using, and I think I've covered those in the past. So let's have a look at this memory view here. In the memory view on the right hand side there, we can see that the color RAM updates are going on. Well, actually it's color RAM reads. Now this is interesting because color RAM is actually not used in the bitmap display mode, in the high resolution bitmap display mode, because the bitmap high resolution display mode gets its colors for each character cell from what would normally be the screen character map. So this is actually a good Spectrum conversion, is that it uses the hardware capabilities of the Commodore 64 to improve the game, which I actually quite like. It means that some real thought has gone into this. Now you can see how the bitmap screen, when I go between the different screens there in the map, you can see how the bitmap screen is being updated. So let's set a ranged watch store point for memory updating the bitmap data for the middle, or roughly the middle of the screen, so we can see. So we know that the bitmap screen starts at 6,000 in hex. So let's just fill 7,000 to 7,200, and that's the memory that we want to watch for. That's just the visible memory range. So when I flick to the next map, we can see that we're running some code, and this code here, if we go to the disassembly view, let's open up the disassembly view and have a look to see what, yeah, this is an optimized, kind of almost unrolled, but not quite speed code, or not quite speed code. It's still got the indexed, Y stores there, but that's a memory clear. So this is clearing the bitmap. We're not really interested in how the bitmap is cleared. What we're really interested in is understanding how this screen update draw actually happens. So let's see if we can find the code where the block draw happens. Okay, so we're at this point in the code here and looking at the CPU history. it's not telling us a great deal of information at this particular point in time. We do have, okay, so we went to the left, and that means that the x coordinate should be decremented, and we've got this decrement with B9 here. So let's update the debugging details text file. Now, this debugging text file, like I always do, that I will commit to source control, so you can see my own debugging notes, and you can read through what I've been working on. But yes, we're moving left. This code at D18 seems to decrement B9 just before redrawing the screen. So maybe B9, and B9 on its own is an 8-bit value. It's a byte. So that only stores values between 0 to 255. But we've got 512 screens, so I expect BA is also going to be like the high byte, if you like, of the room or the map coordinates. So we'll see where that comes in a little bit later on. So let's put a breakpoint at that memory range, at that memory address. So we've got 410A there, which is after the screen clear. So this is interesting. It's doing a load with 1, anding it with FD, and then storing it back in 1 again. That switches off all of the kernel ROM and everything like that. It exposes the RAM underneath. Then it's doing a load A with E0, storing it in 7.9 and 7.8. Okay, so 7.8 and 7.9 is setting up what looks like a low and high address bytes for E000. So there's probably some data at E000 that we'll want to have a look at. Oh look, it's at E8C there. It's loading accumulator with B9, and then it's also loading BA as well. So B9 and BA looks like it loads the map coordinates or room number, which is a value between 0 and 511, because we've got 512 screens in this game. So let's keep on tracing through this code to see what we can find. This code here seems to take the room number or map coordinate and then multiply it by at least 2, maybe 4, and then calculates an address into 7.8 and 7.9 in 0 page, and 7.8 and 7.9 in 0 page seems to point to a particular place in memory, which is in this case E028. If we have a look at the memory at E028, so this is C, D, E, and F, so it's going to be in the middle part. That does look like structured data, right? With maybe, because of those black columns of pixels, it means that the high bits are probably not set in that data, so it looks like structured data of some sort. Looks like an address calculation routine here. Then stepping into the next. So this is the address calculation routine, and then the next JSR to 1037 here seems to be initializing, well, 4 bytes of data, and then it seems to be doing some repeated calculations on the passed in and what I think is the multiplied up room number or map offset or something like that. So, you know, my hypothesis at the moment is that maybe this is some kind of like random seed preparation routine, because to draw these levels there might be some kind of like procedural data or something like that, or maybe it's some kind of bit twiddling or bit shifting calculation routine which aids in the map draw later on. Let's investigate further. Let's keep on stepping through this map draw code. Oh look, it's just drawn a block in the top left hand corner. This block seems to be 4x4 character cells, but in a bitmap screen mode. So something is going to be telling it to draw this block. we need to keep on tracing through this code to see what was doing that. But yeah, 10B0 seems to be a 4x4 character cell block draw, and it's obviously copying that information from somewhere else in memory. This draw loop, so it's loading from 7.6 and 7.7 in indirected memory, which is pointing at F800 all the way up at the top of memory. So again, let's have a look at the data all the way up at the top of memory. Yeah, again, this seems to be kind of like structured data, doesn't it? The bit patterns which are visible in the bitmap display there are not bitmap data, but they're very well structured, very regularly structured. So loading a 4x4 block number from that memory range up at F800 and then JSRing to 10B0, which is the 4x4 character cell block draw, is very much indicating that we've got this loop going through and actually drawing these blocks based on data which is currently loaded from F800 onwards. Stepping through this drawing code, we've got another map block being drawn there on the screen, and then so it's drawing an empty block, and then the next draw comes along, and then so it's drawing a block above, and then it's drawing a block to the left. So it seems to be okay, so it drew a whole column of 4x4 blocks, but now it seems to be drawing a block of 2x2 tiles, no, blocks, which are then 4x4 character cells. Okay. So it seems to be that maybe the memory at F800 is what we would like to call meta tiles, perhaps. So that each, yeah, look, if I keep on going through, we can see that the 4x4 blocks are actually grouped in 2x2 larger blocks or meta tiles. And then these meta tiles are then read from somewhere. So it seems to be two levels of indirection. There seems to be a map, which then points to a meta tile, which is 2x2 blocks, and each block is 4x4 character cells. Well, that kind of explains, I think, how this game stores such a large amount of data. Just before it starts drawing the map, let's override B9 and BA with 0 and 0. This should be the first or 0 room. And yeah, look, if we step through the drawing code here, and we have the screen drawn, we can compare it with the map of admittedly the Spectrum version. So let's bring up there's the map from the Spectrum version in the web page, and then we bring up the graphics map debug view, and we can see that this rendered view on the Commodore 64 basically matches the screen up in the top left-hand corner of the map view from the Spectrum map. There's actually an extra column of blocks on the left and an extra column of blocks on the right, and I think that's actually coming from the adjacent screens. So I think the Commodore 64 view is actually, potentially larger than the Spectrum screen view or something like that, maybe, potentially. Anyway, yeah, so we have the same map. So yes, B9 and BA are definitely the map room number, if you like, or the screen number, and then it goes through all of this draw code. So I've added some labels, so that's why you can see the labels in the disassembly there. I've added some label names for those memory addresses to help understand what this code looks like. So we've got calc map data from coordinates, for example, get y map coordinate, draw map column, and all of the other support routines as well. This really helps when reading the disassembly, of course, and trying to understand it. Let's find out the memory address that starts to be read in the map for room number 1. So we'll override that in B9 with 10, which is low and high bytes. So that's room number 1. This first pass through calc map data from coordinates gives us an address of E004, but it's doing it twice because I think that it's multiplying it by a non-power of 2 number. So the next iteration through this is, so the first time round it multiplies the room number by 4, and then because of the shifts and the rotates, there are 2 pairs of them, which is 2 times 2, which is 4. And then the next time it runs calc map data from coordinates, it's multiplying it or shifting it and rotating left by 2 again, which is multiplying it by 8. But it's adding 4 and 8 together to give 12. Look, E00C, and C is 12 in decimal. So room number 1 reads from E00C, which is the next room over in the map data. So each room uses at least 12 bytes of map data, and those 12 bytes then translate into the 2x2 meta tiles, which then translates into 2x2 times 4x4 character cell blocks to then draw the main part of the screen. Let's just set up room number 2, or map room number 2 there in B9, and then we'll just step over this calc map data from coordinates stuff over there, and then we'll test the next map address, which is 78 and 79, and that's E018 in hex, which is 12 plus 12, that's 24, or in decimal, or 18 in hex. So yeah, I think we can safely say definitely that each room in the map uses those 12 bytes, which then translate into those meta tiles, which then translate into the 4x4 blocks being drawn. So let's really test this hypothesis by first overriding the room number to be 0, and then poking in 12 bytes of 0 into E0000, which should be the map data for the first room, and then let it draw and see what we get. That's not the first room. Let's really make sure that we override the map. There we go, there's the first room. And yeah, it's drawn blank apart from the left and right hand columns, which I think come from the adjacent room data. So there we go. I think we can safely say that we can update the map. Let's just test this a little bit more by updating it with different bytes, shall we? This is our current empty room now in the top left-hand corner of the map. Ignore the columns on the left-hand right. Let's change what we think is going to be the map data now for the screen to the right, which is room number 1, or map screen number 1. So that's going to be 12 bytes onwards, or E00C in hex. Let's change it so we can have a nice repeating pattern of 0 and 1 meta tiles. Let's fill that memory there, see what we get. Okay, so we've got a blank screen. Maybe map blocks 0 and 1 are empty tiles. Let's fill the first map with blocks or map meta tiles 2 and 3 in a nice repeating pattern, and then let the game, that's better, isn't it? So yes, so meta tiles 2 and 3 are basically different configurations of background star patterns. Okay, that's good. So let's use the fill command with a suitable memory range, right? So that's going to be, what is it? E00C plus another C, which is going to be E018, isn't it? Yes, there we go. So E017, we want to fill it with 2 and 3 in the adjacent screen. No, we'll fill it with 4 and 5, I think. Yeah, let's fill it with different meta tiles just to see if we can see anything different. And okay, there we go, got stuck in the background stars. And then if we go back Let's see what we get. Okay, so we seem to have... Is that a different star pattern? I think it is, right? I think the arrangement of stars looks different. Let's change it to meta tiles 6 and 7. So let's go to... there we go. That's definitely different star patterns this time, right? So those meta tiles are definitely different. Yeah. So, yeah, basically we're able to update the map screens by updating the memory at E00C or E000 onwards, with 12 bytes being used for each map screen. With this memory layout, I think that means that we have 512 times 12 bytes. That's 6,144 bytes for the map data, and it uses probably the F800 onwards memory range. So that's going to be maybe a kilobyte or 2 kilobytes, 2048 bytes maybe for the meta tile information. So actually it's about 6, 7, 8 kilobytes for the map data, not including the 4x4 block data, but I think that's being copied from somewhere else in memory. So actually this game was able to store 512 screens using this meta tile arrangement quite efficiently. I think maybe the data could have benefited from a different form of compression, but you know, it fits in the memory, so I think it's perfectly adequate. I think we'll leave this video here, and I think that's what I basically wanted to cover. I wanted to cover the question that was asked in my YouTube comments section about this game and how it managed to store so much information. As always, I will add a link to the debugging notes text file in my GitHub repository, and I'll put a link in the video description below. If you like these kind of retro games, deep technical dive videos, then please do consider liking or subscribing to this channel, and a super thanks is always very much appreciated. Thank you very much for watching, take care, have a great day, evening or night, wherever you are, and I'll leave you with the music for this game.